PhD student that you will be, Androniki Dimitriou and Brian Zaldivar, which are both in IFIC in Valencia, in Spain, and I will continue discussing that later on. So, there is a question? No? Okay. So, I mean, so this talk is about dark matter, and I guess that most of you know about dark matter, but I will have a very short introduction to it, just to remind you that, I mean, we first got to know about the dark matter problem, let's say, by looking at motion of galaxies into clusters of galaxies, and then essentially stars into galaxies. All these told us that we had some missing mass. Now combining large-scale structures, CMB anisotropies, and supernovae data, we get to this chocolate pie version of the energy content of the universe, where you have few baryons, a little bit more dark matter, and a lot of dark energy. But what is of interest here is that you have essentially 80% of the matter content of the universe that is made of dark matter, and we don't know its exact properties. So what is the nature of dark matter? What we know is that it should essentially be neutral, massive, and it cannot be a particle of the standard model. Beyond that, we have a lot of possibilities. Just looking at the mass range, we can go from masses between 10 to the minus 20 electron volt, considering particles, up to solar mass, primordial black holes, let's say. I mean, or even more than solar masses. So at the end of the day, in this talk, I'm going to focus actually on particle dark matter, and in an energy range going from few electron volts, excuse me, to say a few hundreds of GeV. Is there a question? No? Okay. So there are many imprint of dark matter that we can look for in cosmology. I'm sorry, I'm going to cough again, so I'm going to get some water. And among those imprints, I'm going to focus on two particular ones, which is the possibility for dark matter to inject energy into the medium. This could be due to decaying dark matter, annihilating dark matter, thinking beyond particle physics, like creating black holes. Energy injections are known to do a bunch of effects, like, for example, affecting the cosmic microwave background at the level of cosmology. And my question here will be, can we get further constraint from what I call the 21 centimeter cosmology data? On the other hand, another effect I will consider is the possibility for dark matter to delay structural formation due to its non-cold nature. The most standard suspect for non-cold dark matter is thermal warm dark matter. I will go back to this. Current strongest constraint on the mass of this particle, if I'm thinking of thermal warm dark matter, comes from Lyman alpha forest data. And I will also check if actually, again, 21 centimeter cosmology can tell us more about this. Just to give you more concrete example and to, let's say, tell you a little bit more on what I'm going to focus, I'm going to actually really focus on decaying dark matter. And in particular, I'm going to show you that 21 centimeter cosmology is nice in order to get further constraint on action-like particle decaying to a pair of photon. Usually, you can represent constraint on the parameter space of this kind of particle in the plane of its coupling to a pair of photon, which is dimension full, and its mass. And actually, in particular, in the range of a few electron volts to hundreds of electron volts, you can see here that there is a constraint that is referred to as ionized fraction. So it's actually a constraint from an old constraint from CMB, and I'm exactly going to show that what we can do with 21 centimeter cosmology in that exact range. About non-cold dark matter, So I mentioned thermal warm dark matter, but actually there are other particles that can behave like non-cold dark matter. As an example here, I just show you the parameter space of a dark matter candidate that would be obtaining its relic density through freezing. It's a feebly interacting massive particle that couples to the top and colored scalar. And I show you in the plane of the mass difference between, say, a heavy mediator that would decay into the dark matter. So this is the mass difference between the heavy mediator and the dark matter, and the coupling of the dark matter to this heavy mediator. So you see very suppressed coupling between 10 to the minus 6, 10 to the minus 12, that could give rise to the right radical abundance through freeze-in and super-WIMP actually. What you see in this plane is that because this particle is coupling to colored particle, you can actually have constraint from particle physics experiments, collider, in this part of the parameter space. But you can close, let's say, surround the parameter space, the viable parameter space of this particle by considering constraints from cosmology. So I'm really interested here into the complementarity between cosmology and particle physics and how this can really help to, let's say, understand better the nature of dark matter. So I repeated several times 21 centimeter cosmology, and I would like to tell you a little bit more what this could be. So the signal we are interested in arises from spin-flip transition of neutral hydrogen. These are transition between the two ground state energy level of neutral hydrogen that give rise to emission or absorption of photons of a wavelength of 21 centimeter. This is the origin of the name. But I mean, 21 centimeter wavelength corresponds to a frequency of 1,420 megahertz. Actually, we are going to look at this kind of signal arising from epoch, which are not today. They are epoch from cosmic dawn and epoch of ionization, say redshift between 30 and 10. And actually, the signal is going to be redshifted from frequencies of 1,420 megahertz to hundreds of megahertz, which are actually possible to probe with a radio telescope on Earth, and could help us to probe the part of the history of the universe, some part of the history of the universe, between the one that can be probed by galaxy survey today and cosmic microwave background at much later time. What is exactly the signal I'm interested in? So I'm just going to do an analogy. You know, cosmic microwave background, you know that we have a beautiful black body spectrum on the top of which we have fluctuation of temperature, and we look at its the power spectrum of temperature fluctuation. In the case of 21 centimeter cosmology, we are looking at a signal that arises from later redshift. So this is redshift 1000, redshift 30 to 10. But we have also the possibility to have access to, let's say, an average signal over the sky, the equivalent of the black body spectrum. And over the top of this, we can also have access actually to power spectrum of fluctuation, not only in the direction of, like, let's say, the angle of the sky, as in the case of cosmic microwave background, but also as a function of redshift. In order to get access to this signal that is particularly interesting because it is expected to have a high signal to noise ratio, we are going to make use of telescope arrays such as the Hera telescope, which is already fully built in South Africa. How it works in practice, what you need is first a background radio source. You need clouds of neutral hydrogen, and you look at the signal after going through these clouds. Our source is actually cosmic microwave background in this case. This radio signal is going to pass through neutral hydrogen clouds, give rise to some emission or absorptions, and we are going to look at the difference between the signal after the clouds and before the cloud. Yes? There was a question? I suspect that there are some microphones that are on. Maybe it would be good to close it and just open it when you have a question. Thank you. So what does 21 centimeter signal corresponds to is actually spectral distortion of the cosmic microwave background. Now you will tell me, if I looked at the intensity of the signal as a function of the frequency, essentially I expect to have a beautiful blackbody spectrum that is very well tested, for example, by Kobe, Firas, and Arcad. Actually, this is true in some range of frequencies, but I told you I'm interested in frequencies of the order of hundreds of megahertz compared to the range of frequencies that are well tested, which are above 1 gigahertz. Okay, so I'm looking at spectral distortion in that region. This signal is actually going to be characterized by a bunch of temperature. The temperature of the source, which is the CMB in our case. The so-called spin temperature that is going to characterize the relative occupancy of the two ground state energy level of neutral hydrogen, so spin temperature here. And at the end of the day, we are interested in the brightness of a cloud of neutral hydrogen with respect to the source. This is expressed in terms of the differential brightness temperature, which depend on the parameter I already mentioned before. So the temperature of the source, the spin temperature characterizing the relative occupancy of the two ground state energy level, and the relative fraction of neutral hydrogen. No neutral hydrogen, obviously, no signal anymore. Any question up to here? No. Okay. So as I mentioned, we have the CMB temperatures that you see here, the temperature as a function of time between redshift, say, of 0 and 30, which is the region of redshift that I'm interested in. CMB temperature just scale as 1 over A. Gas temperature as decoupled from the CMB temperature at redshift of the order of 150, and since then has been scaling as 1 over A square. So they are separated from each other, okay? And here in the between, you see the spin temperature. Actually, in order to know what is the value of the spin temperature, you should essentially solve Boltzmann equations that would tell you how different processes, such as absorption and emission of CMB photon, or resonant Lyman alpha scattering, which essentially are going to give rise to transition from the ground state energy level, go to the first excited state, and go back to the ground state energy level, potentially into a different ground state energy level, so indirectly inducing spin flip transition. So these kind of processes could actually modify the spin temperature. At the end of the day, the spin temperature is given by a rather simple expression that tells you that in the range of redshift that we are interested in, the spin temperature should either be equal to the CMB temperature when emission and absorption of CMB photon is driving the signal, is sourcing essentially, is inducing the spin flip transition, or by the gas temperature when scattering of Lyman alpha photon is inducing mostly the spin flip transition, which are naturally rather happen with a very low frequency. Okay. This is the temperature, and I want to go to the differential brightness temperature. What you see is that the differential brightness temperature, that I should remind you, was appearing as 1 minus this temperature of the source divided by the spin temperature, is obviously going to depend on these quantities that I showed here as a function of redshift. When spin temperature is sticking to the gas temperature and below the CMB temperature, the differential brightness temperature is going to be negative, and essentially the signal is seen in absorption with respect to the CMB. At later times, when the first, let's say, stars emitting X-rays hitting the medium so much that it has temperature higher than the CMB temperature, the differential brightness temperature is going to be seen in emission with respect to the CMB. At later times, a redshift around, let's say, 6 or 8 here in this simulated situation with a certain assumption, you end up with no more signal around redshift 6 because you have no more neutral hydrogen. This
Laura,
was, yes.
Sorry,
yes.
Could you explain the factors that you have in this expression above? Because
Here?
the spin temperature depends, yes, on XC, X alpha.
Yeah, so this factor essentially represents the coupling of the gas, sorry, the coupling, the importance of the coupling of the spin temperature to the gas temperature. Tk and Tc are actually both essentially the gas temperature. This is essentially a function of the scattering cross-section due to collision with hydrogen and electron that would give rise to what would induce spin flip transition. And same here. I mean, they essentially give you how probable is the scattering of the Lyman alpha photon that is going to essentially induce make it such that this term is gonna become the most important one.
Okay. Okay. So you have 3 contributions.
Yeah.
To the spin. Okay.
I mean, 3 contributions to your Boltzmann equation have 3 terms of interaction, let's say, okay? One that is due to emission absorption of the CMB, one to collision with electron and helium that could give actually rise to also spin flip transition, but not in the range of temperature that we are interested in, and scattering of Lyman alpha photon. So you have these 3 terms, okay? And you can rewrite, I mean, in an equilibrium situation, the spin temperature are just some kind of, let's say, I forgot the name, there is a name for that, but equilibrium equation, let's say, where you see that the spin temperature can be rewritten as a simple expression where when these terms become bigger than the others, I mean, everything is going to be driven by collision with other atoms or electrons. And when this X alpha becomes big, it's going to be driven by this term. And the spin temperature is going to be equal to the color temperature, which at the end of the day is equal to the gas temperature. Okay?
Okay, thanks.
No problem, thank you. So, I mean, you might remember that there was an experiment, the EDGES experiment, that claimed some very strong absorption into the differential brightness temperature. This raised a lot of interest into this analysis. It also showed up to which point the foregrounds are very difficult to extract when you are looking at the signal that is averaged over the sky. So this differential brightness temperature, which as a function of the redshift, which is the equivalent, if you want, of your black body signal of the CMB as a function of the frequency. Now, as I said, we can look at fluctuations on this signal, and we are allowed to consider the variance of this fluctuation, or the power spectrum of fluctuations. And notice that, interestingly, here I show you the power spectrum as a function of redshift. If you think of the CMB, you usually see the power spectrum as a function of the multipole, or equivalently the angle in the sky. If you think of the power spectrum of matter, you usually see it as a function of the wave number, the inverse of a scale. The point of 21 centimeter cosmology is that I could actually plot this power spectrum as a function of the scale for a fixed redshift, or as a function of the redshift for a fixed scale, which I did here. Okay. When I show you and I mean, this is really the power of 21 centimeter cosmology, is that you really have access to a volume of information which is much bigger than just looking at one slice, I mean, at one moment in the sky when you are looking at CMB information at a given around, let's say, redshift 1000. So you see that there are 3 peaks that you can expect to see for a certain scale. So I think here it was around 0.1 inverse megaparsec. And these 3 peaks, actually, they are corresponding to the different epochs that I was mentioning before. So remember, I told you that the Lyman alpha coupling is going to be responsible. I mean, Lyman alpha, the resonant Lyman alpha coupling is going to induce a spin flip transition and essentially couple the spin temperature to the gas temperature. When this process starts to be very important, you are going to see a peak in the power spectrum fluctuation. You have a second peak when actually X-ray heating is going to drive the source of the fluctuation in the power spectrum, and you have a final peak when actually reionization is taking place. Okay, and what happens is that if you change the parameter, the astrophysics parameter, giving rise to X-ray heating, reionization, or Lyman alpha photon emission, you are obviously going to change the shape of the spectrum, and actually your dark matter properties can also change the shape of the spectrum, and this is what we are interested in. Currently, we don't have observed, we didn't observe yet the 21 centimeter power spectrum, but we have upper bound on its value. So here I show you again this power spectrum as a function of the redshift. I mean, I show you, I took this from some review, and you see some example of power spectra depending on the astrophysics model that they had been considering. And you see that here you have upper bound from different experiments. In particular, I was mentioning before that we have this Hera telescope, which is fully built currently, but we don't have data from the fully built experiment. It's rather recent. I mean, in 22, they provided an analysis where they used 70 antenna out of the 331 that are now fully set up. And they have used 94 nights of observation, and with this, they could put the strongest upper bound in the corresponding redshift. I mean, at redshift, say 8 and I don't know, 10.5 or something. They could essentially put new upper bound on the power spectrum. So the reason why we are interested into Hera is because it's one of the first that is expected to be approaching the 21 centimeter power spectrum or detecting, hopefully in the near future. Any question about 21 centimeter cosmology before I move to dark matter energy injection? Any further question? Okay. I will go back to dark matter and things that you might already know of. You might know that dark matter can inject energy in the universe through whatever, decays, annihilation. And I'm personally going to focus on decays and annihilation into standard model particles. This could be any kind of fermions, photons, WZ, whatever you like. The point is that all these particles, at the end of the day, they are going to hadronize, decay, and give rise to electrons, positrons, photons, also neutrinos, which will not affect directly, or I mean, in a very suppressed way. So actually in this talk, I will focus, when I'm talking about dark matter energy injection into electron-positron pair and photons. For example, the decay of the alpine into photons. For the rate of energy deposition, this depends on the dark matter nature. I told you I'm going to decay, I'm going to focus on dark matter decays, in which case the energy injection goes as the dark matter density divided by the lifetime of dark matter. But we could look at dark matter annihilation, in which case it goes as the squared of the energy density times the annihilation cross-section. For P-wave dark matter, P-wave annihilating dark matter, will have a velocity contribution that would change the situation. And thinking beyond particle physics, we could also have energy injection through accretion, in which case it would depend on the number density of primordial black hole time, the rate of accretion. Just to clarify why I'm going to look at decaying dark matter, the reason for this is because we were expecting that decaying dark matter is more exciting than annihilating dark matter in the case of an exciting anesia. in the case of 21 centimeter cosmology. And the reason is as follows. If I look at the energy injection per unit baryons per redshift, I mean, the exact form is still rho divided by the lifetime, the energy density divided by the lifetime, plus some factors here that goes with the rate of the expansion of the universe. I plug the dependency in redshift of all these quantities, and I get that this energy injection per unit redshift goes as 1 plus z to the power minus 5/2. If I was looking at energy injection from dark matter annihilation, this goes as rho square, meaning that I change the power in redshift here, and I get to a dependency in redshift that goes as 1 plus z to the power plus 1/2. The difference here, the main difference you should be looking at is that one goes as positive power of redshift, the other one goes as negative powers of redshift. This means in particular that dark matter annihilation is already affecting probes at high redshift in a very efficient way. This is not the case of dark matter decays. It's essentially a late energy injection. So at the end of the day, the point is that, for example, for dark matter annihilation through S-wave annihilation, it's already well known that, for example, CMB gives strong constraints on dark matter properties. In the case of dark matter decays, CMB bounds for dark matter decays into electron positrons or whatever is typically getting something like 10 to the 24 second at 95% confidence level. If you compare to indirect dark matter searches, this is very bad. Indirect dark matter searches, they probe to lifetimes of 10 to the 27, 10 to the 32nd. Now, this is what I'm saying here is not completely true. Actually, you can go back to our ALP decays in the range of few electron volts to hundreds of electron volts. Actually, this is exactly where X-rays stop to be very constraining, and where CMB constraint can become stronger and can become competitive with astrophysics constraint. And actually, for dark matter, for example, decaying to electron positrons for a mass smaller than a few MeV, you can probe with CMB lifetime up to 10 to the 26 second at 95% confidence level and become the strongest constraint. Now, okay, very good. Let's remember this 10 to the 26 as the best case, the best lifetime that we can probe with existing cosmology probe, and see if we can do better with future one. I go back to my plot of temperature as a function of the redshift and differential brightness temperature as a function of redshift. Remember, we have the CMB temperature that goes down, gas temperature that is a little bit below, and spin temperature that is in between. It's in blue. Due to this plot, I get essentially an absorption feature around somewhere between redshift 10 and 12. Okay, this is my fiducial scenario. Now let me add dark matter that would decay, for example, into a pair of electron positron for a mass of dark matter of 10 MeV, and lifetimes between 10 to the 27 and 10 to the 26, corresponding to two different colors here. And let's see what happened. What you see is that the temperature of the gas is going to be heated. It goes up, like up with a step, okay? When you do that, obviously, the spin temperature is going to go down less. And because the difference between the spin temperature and the CMB temperature is not anymore so big, you have less absorption into your global signal, okay? Now, this is not what we are interested in. We are interested in the power spectrum, which is the one that is expected to give a higher signal to noise ratio. So this is actually the 21 centimeter signal as seen by Hera. So beamed in redshift beams as Hera is capable to do for a fixed scale of 0.18 1/megaparsec as a function of the redshift. The gray bands essentially inform you on the sensitivity on the Hera experiment. You are no more sensitive to the signal beyond, say, something like 15 within the setup considered here. What happened when I add to this fiducial scenario, which was the black line, I add energy injection from my dark matter that decays that was giving rise to a suppressed absorption here, what you do is that you suppress the power spectrum. The reason is that you heat with dark matter uniformly the medium well before the first star did. The stars, they begin to hit the medium here, okay? They don't do this jump here, meaning that you have a more uniformly heated medium, meaning that you have less fluctuation, less variance of fluctuation to suppress the power spectrum, okay? And you see that you can do that with lifetime up to 10 to the 27 seconds, which is already much better than what CMB could do. It looks like we can be sensitive to this effect. Obviously, you have to be careful. You have astrophysics that can do similar effect. This is by changing the X-ray heating. Okay, so what we did is but it's possible to disentangle the different effects. We did a Fisher matrix analysis in order to show the bounds in the plane lifetime versus mass of the dark matter. These are existing CMB bounds, cosmology bounds, sorry. And these are the bounds we get, forecasted bound we get for ERA with 1,000 hours of observation. What you see is that you can essentially improve the constraints by up to 2 orders of magnitude within the setup we considered. Now, by changing astrophysics, you can essentially change this by 1 order of magnitude, but still you can become more constraining than existing indirect detection searches represented in gray for masses below a few MeV. When dark matter decays to a pair of electron-positrons, when dark matter decays to a pair of photons, it's particularly interesting into this range between a few electron volt to MeV, where you see in blue the same constraints as before. So with the blue line is the strongest one, the second blue line is the less strong one, and red color and green color were existing constraints from CMB. Okay, so this looks promising. Let's see if we can do something else, and let's talk about non-cold dark matter. I remind you that non-cold dark matter for me is some kind of generalization of thermal warm dark matter. Thermal warm dark matter is a particle that is in chemical and kinetic equilibrium with the plasma at early time, decouples at some point, free stream, and it's going to, by free streaming, it's going to go from overdense to underdense region and smooth out in homogeneities below free streaming scales that will depend on its mass. Here I show you the Matter power spectrum, actually, as a function of the inverse of the scale is the dimensionless power spectrum. In blue, continuous blue, you see cold dark matter. With dashed line, you see thermal warm dark matter. Small scales are here, large scales are there. At large scale, thermal warm dark matter doesn't change anything. At small scales, it suppresses exponentially the power spectrum. You can have other scenarios that give rise to a suppression. I mentioned for free streaming dark matter, freeze-in, super-WIMP, but you could also suppress the power spectrum by collisional damping for dark matter interacting with light degrees of freedom, such as dark matter, neutrino interaction, and so on. Lyman alpha forest observation that I mentioned already before also can actually already probe the Matter power spectrum in the colored contour here. Currently, so these Lyman alpha forest observations that are essentially considering the Lyman alpha forest's signature into distant quasar due to the gas, which is in between the quasar and us. By this, by observing these lines and looking at their width and their properties, essentially looking at the power spectrum of the transmitted flux. At the end of the day, people have been able to characterize the distribution of small scale matter structure and to put constraint actually on thermal warm dark matter that would erase this small scale structure. Currently, from Lyman alpha forest observation, thermal warm dark matter should be above something like 5.3 keV. What is happening when we are talking about 21 centimeter cosmology is that by changing the power spectrum, the amount of structure at small scales, you are actually going to change the number of halo per unit mass you have at small masses. So here I show you the halo mass function, the number of halo per unit mass as a function of the mass of the halo. The blue line is cold dark matter. The red line is warm dark matter, okay? You have less low mass halos when you have warm dark matter. If you have less low mass halos, this halo mass function that counts the number of halo per unit mass is actually going to play a role in the computation of the number of ionizing photon that will be there to ionize your medium, the X-ray flux and the Lyman alpha flux that you need in order to compute your signal of 21 centimeter. By reducing the number of small mass halo, which are supposed to be numerous, you are going to strongly affect the signal. You are going to suppress the signal. If you suppress the signal, you are going to make that, for example, the 21 centimeter, the spin temperature is going to stick to the gas temperature later. You are going to delay everything, all the features. The point is obviously, as usual, that it's not only that warm dark matter, exotic dark matter physics that can affect in some way, like suppress the contribution of low mass halo. You have to know that actually there exists a threshold mass for star-forming galaxies. Actually, small halos do not form stars. They are not large enough to essentially give rise to star-forming galaxies. This is taken into account in our analysis through a duty factor that is an exponential of minus our threshold mass divided by the mass of the halos. At the end of the day, I go from my original cold dark matter power spectrum, just taking into account this duty cycle, to a suppression of low mass halo. The threshold mass you should consider for the galaxies that we knew up until now, say atomic cooling galaxies, they are expected to typically have a threshold mass around 10 to the 8 solar masses at redshift 10. If you look at such cut in the halo mass function due to these galaxies that do not form stars, you see that if I have such a cut, I will probably never be able to probe the properties of non-cold dark matter, at least a warm dark matter of a mass of 5.3 keV. So what we did was an analysis to try to understand under which condition, in particular, which value of this threshold mass for star-forming galaxies we could, with 21 centimeter cosmology, improve on existing constraint from Lyman alpha forest observations. I already told you, but now I can show you like with an image. So what is the effect of non-cold dark matter on the 21 centimeter signal? So this is the power spectrum. This is the global signal. You see again as a function of redshift. The fiducial scenario is in black, the one considered here. And what happened when you consider fiducial scenario is for cold dark matter in this case. And you see what happened when you consider warm dark matter with different masses. The lower the mass, the hotter is the dark matter, the bigger are the structures that are going to be erased, and essentially the later the 21 centimeter signal is going to show its different feature. Okay, I go from a peak here to a peak that goes there with a 4 keV dark matter. I go from an absorption feature that was around redshift 15 to an absorption feature that goes to something like redshift 11. As I said, not only warm dark matter can do that. You'll see that this is again the effect of thermal warm dark matter going from 30 keV to 2 keV here in green. Here is exactly the same fiducial scenario, but I changed the threshold mass for star-forming galaxies from a threshold mass of 10 to the 5 solar masses that would be representative to molecular cooling galaxies that would host like mini halos that would be hosted into mini halos, and that would give rise to very early star of the type. It would be made of early stars of the type POP3 stars. So let's say it's our lowest allowed value of the threshold mass for star-forming galaxies, and the 10 to the 8 solar masses is the one that is most representative of the the type of galaxies that we have mostly observed currently. Now, actually, in this case, we did not do a Fisher matrix analysis, but we did simulation-based inference analysis, where again we took into account multiple possible astrophysics parameter as well as the warm dark matter mass. We trained a network in order to try to get some forecasts for what would be the warm dark matter mass we would be able to probe as a function of the threshold mass for star-forming galaxies. The excluded Lyman alpha forest constraint is here. Below the dashed line, you're excluded by Lyman alpha. Our analysis for certain parameters of astrophysics and fixed value of the threshold mass tell you that, for example, if you have a threshold mass for star-forming galaxies that is very high, say 9 solar masses, you will never be able to improve with respect to Lyman alpha forest observation. Okay, but I obviously assume that I have a single population of galaxies that would have all these threshold mass for star formation for star-forming galaxies. Now, as soon as I get below something like 8.5 solar masses, the forecasts for 21 centimeter cosmology become more interesting, right? You can improve with respect to Lyman alpha forest constraints, going from a constraint of 5.3 keV to something that can go up to, within this astrophysics setup, up to something like 17 keV. That would be excluded by 21 centimeter cosmology. Actually, as I said, this is for one given setup. If I change, for example, the X-ray properties and I consider X-ray parameter, that would again somehow hit the medium more and suppress the contrast that we would have. It will be more challenging to do whatever, including detecting the properties of warm dark matter. And here you see that in the best case scenario, even if my threshold mass for star-forming galaxies is of size 10 to the 5 solar masses, you see that at the end of the day, at best, I can probe something like warm dark matter with 10 keV. Okay, so I mean, essentially, this is everything I wanted to tell you today. My goal was to try to give you some motivation to go beyond the existing cosmology probe of dark matter. There are multiple possibilities. Obviously, here I focus on the case of 21 centimeter cosmology, and I showed you that at least in the two cases I considered, there are good hope that 21 centimeter power spectrum characterizing the fluctuation in the 21 centimeter signal could help us to improve on existing constraints, both from cosmology and particle physics experiment, or give a complementary, very interesting probe. So thank you very much for your attention, and if you have other questions, please do not hesitate.
Thank you very much, Laura, for the very nice and very complete talk. Question from the audience?
I have a quick question. Thank you for the very nice talk.
Thank you.
On slide 14, you were talking about how there were different peaks in the power spectrum, depending on when the Lyman alpha coupling becomes important, the X-ray heating becomes important, and reionization becomes important. It's not clear to me why you would expect a peak in the power spectrum for each of these different epochs. Maybe you can give some intuition.
Exactly. So essentially, you have to look at the differential brightness temperature that is here, okay? And you have to imagine that you have to perturb this differential brightness temperature, okay? If I perturb this thing, I'm going to have perturbation from the ionized fraction, the neutral fraction, which is 1 minus the ionized fraction, okay? I'm going to perturb the CMB temperature. I'm going to perturb the spin temperature. This is super small, actually, and completely negligible. At the end of the day, what is going to drive everything is perturbation in the spin temperature and perturbation in the ionized fraction, okay? When you have big fluctuation in the ionized fraction due to reionization that is happening, you can expect that the most important contribution to your power spectrum is going to come from delta XH to the square, okay? This is this contribution. Here is when actually the strongest contribution to delta T square comes from actually delta T spin square, which is actually delta temperature temperature of the gas square that is driven by the X-ray heating, okay? And same thing for Lyman alpha coupling. Actually, spin temperature is driven by Lyman alpha coupling here, okay? When you have big fluctuation here, actually, okay, you are going to get a peak here. Does this answer your question?
Yeah, that's perfectly clear. So the two peaks on the right correspond to the steepest gradient of the differential brightness temperature, and the peak on the left is corresponding to the biggest change in the ionization fraction due to reionization.
Sorry, you said in the spin temperature for the two peaks here?
Yes. Well,
yes.
Well, the biggest change in the differential brightness temperature. The
they are all arising from the big peak in the differential brightness temperature, but those can be driven either by fluctuation in in the neutral fraction, okay, or from peaks in the spin temperature fluctuations, okay.
Okay, yeah, that's very clear. Thank you.
Okay, thank you.
Any more questions from the audience?
Laura, could you say again why did you consider or you prefer to consider decays instead of annihilation of dark matter in your analysis?
Yeah, the reason is that so I have hidden some stuff below the carpet. Huh? This is not completely bad story. So the reason why I did is because, if you look at, forget about this term first, okay? Mm-hmm. If I look at dark matter energy injection, it should obviously go as the rate of energy injection, that is the rho squared times sigma in the case of dark matter annihilation, and rho divided by lifetime in the case of decays, okay? Mm-hmm. Rho goes as 1 plus z to the minus 3, okay? So you expect to have a 1 plus z cube difference in between the two, okay? And no, sorry, 1 plus z to the cube. It's a to the minus 3, 1 plus z to the cube, okay? So this is why, at the end of the day, this has negative power, okay? And this has positive power of the redshift, okay? So now let's fix myself at redshift 1000. This is big number, this is small number, okay? You agree?
Mm-hmm. Yes.
Oh, big number. Okay. Let's call a cat obviously. Some non-negligible number, some negligible number. So what happened at the end of the day is what you see is that, let's consider 3 10 to the minus 26 centimeter cube per second for 100 MeV dark matter annihilating to a pair of photon. You see that your ionized fraction is going to jump because of energy injection that are going to give rise to in the case of ionized fraction, going to give rise to extra ionization of my medium. I jump from 10 to the minus 4 to beam 10 to the minus 2. Okay. Then let's take my lifetime, which would be 10 to the 25 second, for example, which is already larger than 10 to the 24. I go from 10 to the -4 to, 10 to the -2. So at the but here the effect is much more strong. Okay, because at low redshift, this is gonna win with respect to that. Okay, so it means that actually decaying dark matter is expected to get better constrained by default than annihilating dark matter when you have a late time probe. So this is why I was interested to go to decaying dark matter instead of annihilating dark matter for looking at the potential of 21 centimeter cosmology. Does that answer your question?
In principle, or in other words, you say that annihilation in the S wave would be a more boring case?
Okay, alors, it's not completely true because I obviously didn't talk about this prefactor, okay? The point is that this prefactor is the boost from structure at late times. When you have structure that form, you obviously have more probability than two particles that meet, and this is why you have this extra increase here, okay?
Mm-hmm.
And this means so that dark matter annihilation is not, that it cannot be probed by 21 centimeter cosmology. It is possible it can be probed. Problem is that you have to deal with this factor, and this gives rise to extra uncertainties in your calculation. It's much more complicated. So we focus on that one.
Okay. Yeah.
Okay.
Maybe what about if you introduce Sommerfeld effects or some?
I mean, you will be already you will be already killed by CMB. You will be already killed by CMB constraints.
Okay.
So I mean, you could. I mean, there is. So the only way you would you can actually win with respect to CMB is to look at something that is very small at early time and much more bigger at late times. And this is the case, for example, of P-wave annihilating dark matter, because velocities at time of CMB is very small, and here it gets enhanced because on the top of this, it increases into virialized halos, okay? So this would be another late time probe that would be cool to, a late time injection that would be cool to look at. But again, the difficulty there is the boost factor. And already dealing with S-wave annihilation and boost factor is a pain in the ass. Dealing with P-wave is even worse. So we decided to focus on decaying dark matter.
All right, yeah.
I mean, it's just that it can be done, but we wanted to have just, I mean, to know if it was worth just looking at it. And this is why we focused on decays.
Okay. My last question is, when you showed this comparison between cold dark matter and 3 scenarios of warm dark matter for this power spectrum.
Yes. This one?
No, it was another one.
Sorry. This one?
Yes, here. So in the bottom, the black line, you said that is your fiducial.
I mean, in all cases, the black line is always the fiducial, meaning is that is my original scenario. And the only thing I change from that scenario is actually the nature of dark matter, that I go from cold to warm dark matter, and I see how things shift.
But my question is, this brightness temperature has been measured?
No. I mean, there are claims of being measured, but I mean, there is nothing that confirms these claims. And they are very fuzzy. I mean, it's very difficult. I mean, essentially, the absorption through from edges is not possible to explain by any physics up until now, okay? The easiest way to explain this is that there is a problem with foreground extraction, which has nothing to do with exotic astrophysics or exotic particle physics. The point is that up until now, the edges observation has not been fully, let's say, how do you say? No experiment has been able to say we see something else, or we don't see anything there, okay, because they could not probe the entire range of frequencies. But Sarah's is another experiment, another one-dish experiment that is currently trying to probe. There are a bunch of other ones, and on the top of this, some scenarios that were used to try to explain the absorption through of edges are already discarded by this first analysis of edges. Of HERA. So I don't know if I have put the HERA paper. Sorry, it's not here. I hope I put it. Yes, in these. Okay. Obviously, I didn't put much information, but in their paper of 21 or 22, essentially, they tell you, they give you some scenarios that were claimed as, for example, milli-charged dark matter that are actually completely excluded given the bounds that are here. Okay, so essentially, yes, there was a claim of observation, but a lot of difficulties to account for this observation. And let's say that, as far as I understand from most of the community, this is much more seen as a potential problem from extracting the foreground within the edges experiment than really a signal.
Okay. Thank you for your presentation, Laura.
No problem. Any other question?
Question from the audience? If there are no more questions, we thank Laura for the very nice and very complete seminar. Thank you so much, Laura, for the very nice seminar.
Bye-bye.
Bye, and we will
Laura.
end the seminar. Bye-bye.
Thank you, Antonio. Bye-bye.
Bye-bye.
Thank you.
Thank you.